Good morning. Today we're going over our first assignment on lipids. So this is going to cover fatty acids, which are a building block of many of our lipids, waxes, and eicosanoids. So here we go. First of all, what do lipids do? What are they good for? And we've got a number of options here. They do not catalyze reactions. That would be proteins. That would be enzymes. Short-term energy storage, that's talking about glycogen, which is a sugar, so we can rule that out. Component of cell membranes, yes, they do that. But again, we determined that they don't do catalyzing reactions, so we can eliminate this option. Neurotransmitters, hormones, transport, nope, those are proteins as well. So it looks like by process of elimination, this is our answer. Storage of excess energy, yes, that's fats. Component of cell membranes, yes, that's the lipid bilayer. And chemical messengers, yes, that's hormones, specifically the eicosanoids, local hormones. So that's the one we want. Next, which following solvents might be used to dissolve an oil stain? Oils are nonpolar or fatty. And so like dissolves like. So other nonpolar solvents would be good to dissolve an oil stain, whereas polar or ionic solvents would not be good. So water is very polar, so it would not dissolve an oil stain. CCl4, the CCl bond is a polar bond, but the molecule itself is tetrahedral, so it looks like this. So even though it has polar bonds, it is a non-polar molecule. So that could dissolve an oil stain. A salt solution, salts are ions. Those are highly charged. Those would not play well with a non-polar oil. Benzene, you guys can picture benzene, just carbon and hydrogen bonds. Very non-polar, so that could dissolve an oil stain. And diethyl ether, somewhere in the middle. It has a little bit of polarity, but some non-polarity. I'm going to guess that it might be helpful to dissolve an oil stain, but if they tell me that I'm wrong, that's the one that I would be less sure about. All right. Next, lipids and fatty acids. So fatty acids are these long-chain compounds with one carboxylic acid functional group, big nonpolar section. So they want us to identify which end is the nonpolar end, which end is the polar end. So what we see, polar COs, polar OHs, that's the polar end. Oops. There we go. This is the nonpolar end because the carbon-carbon and carbon-hydrogen bonds are not polar. The carboxylic acid functional group is what makes this the polar end, and the hydrocarbon chain is what makes this the nonpolar end. Okay. When we classify fatty acids as saturated or unsaturated or polyunsaturated, what we mean by saturated, monounsaturated, and polyunsaturated is exactly what we meant when we were talking about double bonds back at the beginning of the semester. That is, a saturated molecule has no carbon-carbon double bonds, and a monounsaturated molecule would have one of those, and a polyunsaturated would have multiples of those. So for the moment, we're going to ignore the carbon-oxygen double bond and see this chain has no carbon-carbon double bond, so that would be a saturated fatty acid. This one also, no double bonds. This molecule has one double bond. That makes it a monounsaturated fatty acid. This one has two, so it is a polyunsaturated fatty acid, and so on and so forth. Note here also how these double bonds are always shown as cis double bonds. That's because in nature, all of our double bonds and fatty acids are cis double bonds, or a vast majority. Okay, now we've got a number of common fatty acids, which are also the ones that I've got on your lecture notes for you guys to memorize. And the question is, how would we rank these based on melting point? And we know two things here. First of all, we know that large molecules are going to have higher melting points. And then second of all, we know that double bonds inhibit the stacking and make for lower melting points. So the saturated fatty acids are going to have the higher melting points, and unsaturated will be lower. And then within the saturated fatty acids, we're going to go based on size, and then again on the unsaturated fatty acids. So highest melting point, stearic, is our largest saturated fatty acid, followed by myristic, and then lauric. So stearic, myristic, then lauric. And then for our unsaturated fatty acids, actually additional units of unsaturation are going to give them lower melting points. And so just as we saw that, for instance, putting one double bond is going to make oleic much lower than stearic, putting 2 is going to make it lower than oleic, and 3 is going to be lower than linoleic. So here's what we get. We're going to put oleic next, followed by 2 double bonds, linoleic, followed by 3 double bonds, linolenic. There we are. All right, caprylic acid is an 8-carbon saturated fatty acid. So I know it has 8 carbons. And it's a fatty acid, so it has a carboxylic acid. And that's it. 8 carbon atoms with a carboxylic acid. No double bonds between carbon atoms because it is saturated. Next, identify them as saturated, mono, poly, omega-3, omega-6. What do we get? We have 1 that makes 8, 9, 10, 11, 12, 13, 14, 15 carbons. Interesting. I have 2 double bonds, so that would be polyunsaturated. And the omega refers to what number of carbon from the end it is. So starting from here, this is 1 plus 4 is 5. That's 6 carbons, so this is a polyunsaturated omega-6 fatty acid. Pardon, I think that's 18. I think I must have miscounted. All right, alpha-linolenic acid. We saw this one just recently, but it's in our lecture notes. So let's pull. Let's see, alpha-linolenic is an 18 carbon, and it's an omega-3, and you can see it's a polyunsaturated, so polyunsaturated omega-3. This one, as you can see, no double bonds, so that would be a saturated fatty acid. And this has 1 double bond, so it is a monounsaturated. Oh, I didn't submit any of these. Next, write the line bond structure for palmitic acid. Palmitic acid is a carbon-16 saturated fatty acid. So this is going to feel a little bit tedious. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Feel free to curve it around just like that. And it did say here, or did not say, that they want to see all hydrogen atoms. So long as we've got 16 carbons, all saturated, carboxylic acid on the end, that should be good. Hooray. Oleic acid is our carbon-18, omega-9 monounsaturated fatty acid. So here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Wait, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I did that to show that that's a cis bond. I'm not entirely sure that mastering chemistry will notice. Let's try that. Again, no hydrogens. We just have 18 carbons with 1 cis double bond. know what? I put that double bond in the wrong spot. I'm glad I double checked. Double bond needs to go there between the 9 and the 10 carbon. Still showing it as cis. Let's try that. There we go. Next, spermaceti. Chemically is cetyl palmitate. It is an ester of palmitic acid and cetyl alcohol. So you have one fatty acid and one alcohol, and we make a simple ester from it. And again, this is going to feel a little bit tedious. We've got palmitic acid, which is carbon 16. So 1, 2, 3, 4. Oh, hang on a second. 16 carbons. Carboxylic acid, and cetyl alcohol is 16 carbon alcohol, so there's 16 carbons plus the alcohol. And if we make an ester between the two, just like we've been doing, we get a new bond between this carbon and that oxygen. That OH ran away with the H, and that should be the ester formed between palmitic acid and cetyl alcohol. Again, it doesn't need to be pretty, just needs to be right. And you can kind of zoom in. I'm using my scroll wheel here to zoom in to give myself enough room to make that work. Next, what kind of lipid is spermaceti? Well, we just looked at that particular problem. How would you classify this? You should tell me that that looks like a wax. Okay, waxes are simple esters of very long chain alcohols and very long chain carboxylic acid. Here's jojoba wax. You use a 22 carbon alcohol and stearic acid. Stearic acid has 18 carbons. There's 18 carbons. Carboxylic acid. Now we need a 22 carbon alcohol. Two carbons, alcohol, and here we go. That's going to be the ester. There we have it. All right. All right, compare this structure with spermaceti, which is given here. Spermaceti, we determined that they had us make C16 alcohol and carboxylic acid. And jojoba wax, we had the 22 alcohol, which is what they said, and a C18 carboxylic acid. So this is the one, just slightly longer for the wax here. Could it replace spermaceti in the cosmetic industry? We hope so, because spermaceti you get from whales and they're endangered. We don't want to keep hunting them. So it is used pretty widely there. All right, what is a wax made up of? You've got a simple ester of a long chain alcohol and one fatty acid. Okay, these other options, esters of glycerols, are all talking about fats. And if you have unsaturated, either identical or predominantly, that's going to be an oil. These would be solid fats if they're saturated. What is not a function of waxes? They don't do energy storage. That's fats. Fats are energy storage. Prevention of water loss by leaves, that's where we get things like palm wax. Structural material in beehives, yes, that's where we get beeswax. Waterproofing of feathers and shorebirds. Yes, that's why shorebirds are particularly susceptible to things like oil spills, because the oil, being lipophilic, will dissolve the waxes on their feathers and then they die. All right, now we're looking at eicosanoids, and eicosanoids are local hormone. Here's one example, thromboxane. It is an eicosanoid. What fatty acid do you think serves as the biological precursor? Well, if you start here, this is your fatty acid, and because here's your carboxylic acid. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 carbon atoms, and 20 carbon atoms looks like it came from arachidonic acid. Next, again, we're looking at the thromboxane eicosanoid, the thromboxane eicosanoid, and we're just going to identify functional groups. Hopefully you recognize that as a carboxylic acid. That is a carbon-carbon double bond, and there's another one of those down here. This is an alcohol functional group. And this carbon has 2 bonds to ethers. That is an acetal. Fancy. Next, which groups are capable of hydrogen bonding from the molecule above? The alcohol and the carboxylic acid both have hydrogens attached to oxygens, so those are both capable of hydrogen bonding. And the carboxylic acid, by definition, is an acid. It is the most acidic. Finally, do you think the molecule is primary, nonpolar, polar, or something in between? Well, given that one carboxylic acid could take 5 carbons with it into the water phase, one alcohol can take 4 carbons. Together, they might be able to take 9 carbons, but this is a 20 carbon chain. So I'm going to say primarily nonpolar, but it is true that I do have some little polar ends on here, so looks like they want something in between. It's definitely soluble in nonpolar solvents, though. All right, eicosanoids, what do? They function as local hormones. Local just means that they act at or near the point where they're actually synthesized. So these are not ones which your body creates to move through the bloodstream and basically do work all over the body. Just in one little spot. And finally, what do local hormones do? Oh, that's what I just said. Act near their point of synthesis. They can be leukotrienes. Those are some local hormones. They are short-lived because they act right where they are synthesized. Prostaglandins are also another category of local hormones. So we better say all of the above. Good thing I didn't hit submit as soon as I saw the first answer. All right, that's it. I hope this was helpful. Have a great day, guys.